My dear students, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome to all your in our International Physics webinar. Today is our 233rd International Physics webinar, and today we'd like to welcome you all to a joint session between our Department of Physics, Pabna University of Science and Technology, and Princeton University, USA. And we have with us here today Dr. Edward Whitten, Professor, School of Natural Sciences, the Institute of Advanced Study, Princeton University, USA. And he has already connected with us. This is a great day for our department, and I think this is a great opportunity for our students and the viewers to learn a lot of things about from him. So, sir, welcome to our webinar and welcome to our university through online. And thanks for accepting our invitation. So, before going to you, I'd like to introduce you with our student and the viewers. So, dear student and viewers, I think you have already come to know the title of the today's International Physics webinar, and title is very exciting. Title is the new observation of black holes, and our speaker is Dr. Edward Whitten, a professor, School of Natural Sciences, the Institute of Advanced Study, Princeton University, USA. Edward Witten is an American mathematical and theoretical physicist. He is currently working as a professor of the School of Natural Sciences, the Institute of Advanced Study, Princeton University, USA. Edward Witten's work exhibits a unique combination of mathematical power and physics insight, and his contribution have significantly enriched both fields. He has greatly contributed to the modern internet string superstrings as a candidate theory for the unification of all known physical interactions. Most recently, he has explored quantum duality, symmetries of field theories, and string theories, opening significant new perspectives on particle physics, string theory, and topology. In 1990, he became the first physicist to be awarded a Fields Medal by the International Mathematical Union, awarded for his 1981 proof of the positive energy theorem in general relativity. He is considered to be the practical founder of M theory. Fields Medal, officially known as International Medal for Outstanding Discoveries in Mathematics, award granted to between 2 and 4 mathematicians for outstanding or seminal research. The Fields Medal is often referred to as the mathematical equivalent of Nobel Prize. You can see his educational background. He has completed his bachelor degree from Brandeis University in 1971 and from the Princeton University in 1974 and PhD also from the Princeton University in 1976. He has started his professional career as a postdoctoral fellow at Harvard University in 1976, and then he joined as a junior fellow at the same university, Harvard Society, in 1977, and as a professor at the Department of Physics, Princeton University in 1980. And currently, he is also working as the Department of Physics of Princeton University as a professor. And this is his honors and award. You can see he got a lot of awards from different organizations and institutes. Membership, and this is his memberships, and this is his publication. So he has more than 300 scientific papers, and I think you have already came to know about his great discovery on string theory. So thanks for all of your patience. Now it's time to go to our speaker. Sir, I'd like to welcome you again, sir. It's your time, sir. You can start your session.
Well, thank you so much for the kind invitation, but two kinds.
It's
I'd
my
like to
pleasure.
thank all the people who are attending this webinar, and I want to apologize for being late and that there were some technical difficulties in making the connection. And finally, I'd like
No
to say that I hope to one day visit your university in person. Hopefully, that will become possible.
Yeah, yeah, that would be very great if you will join directly.
I hope that you're all able to hear. I understand that the sound isn't perfect. I'll try to speak slowly and clearly, but sometimes I forget. So today I'm going to be telling you about new observations of black holes that have been made in the last 6 or 7 years. So Einstein's greatest achievement was his theory of gravity, known as general relativity, which was completed in November 1915. That was while World War I was going on in Europe. Einstein was living in Germany. He never supported the war, so he kept to himself and worked on his theories and completed his theory of gravity a little over a year after the start of the war, actually. Almost immediately, the distinguished mathematician and astronomer Karl Schwarzschild, pictured here, discovered what we now know as the first black hole solution of Einstein's theory. Schwarzschild was in his 40s, and he saw it as his duty to volunteer to serve on the front. So he actually made this discovery while he was serving in the German army on the Eastern Front. At the time, he was one of the few people with the background to understand Einstein's new equations. Today, far more people would be able to understand it, and the basic mathematics and physics, well, it's much more widely taught. But anyway, at age 41, Schwarzschild volunteered for service, and soon after his discovery, he fell ill and died in May 1916 on the Eastern Front. He was not thinking about anything crazy like a black hole. He was just trying to understand in Einstein's theory the gravitational field of an ordinary body like the sun. It took a long time before anyone really understood his solution. So the modern understanding that Schwarzschild's solution describes a black hole, he described the gravitational field of a spherically symmetric body. And if the body is big like the sun, the solution only describes the gravitational field outside of the body. If you have an ordinary body like the sun, the Schwarzschild solution is useful to describe the motion of planets around the sun. But you don't have to worry about black holes. If something with the mass of the sun would shrink and become smaller, eventually, when it's too small, Schwarzschild's solution describes a black hole. But it took decades before anybody really understood that and took it seriously. It was 47 years after Schwarzschild before the next discovery of a black hole solution of Einstein's equations that's important in astronomy. This was done by Roy Kerr of New Zealand. And this picture, of course, is a relatively recent picture, long after he made the discovery in about 1962 or 3. It took a long time for anyone to take seriously the idea of a black hole, and even then, when evidence began to pile up that black holes really do exist in the heavens, the evidence was very indirect. For example, astronomers would see objects so heavy and small that it seemed they must be black holes. And some of these objects emitted huge amounts of energy, which could be explained by the gravitational field of a black hole. If you have a black hole and an object orbiting it and falling in, it speeds up as it falls in, but on its way in, it might emit radiation, or it might collide with some other object and emit radiation. And so some of the energy that goes into massive bodies falling into a black hole can be emitted into energy that escapes outside. So astronomers began to see objects so heavy and small and emitting so much radiation that it seemed they must be black holes. But direct evidence was another matter. That's changed mainly for 2 reasons. One was the observation made by now 6 years ago by the LIGO Observatory in the United States of gravitational waves from colliding black holes. The second was the first close-up photograph of the neighborhood of a black hole, which was released just a little more than a year ago by the Event Horizon Telescope collaboration. Now, it's quite likely you may have already heard about either or both of these advances, but I will try to describe them in a little bit more detail. So I'll tell you about both of these, but I'll start with LIGO and gravitational waves. So I'm going to start by showing a movie, and then we'll discuss what we have seen. The movie is a computer simulation showing what the initial LIGO event would have looked like if you could observe it from a few thousand miles or a few thousand kilometers, rather than actually being a billion light years away as we actually were. So we were so far from it that we were not able to see the light from this event. We only saw the gravitational waves. But this is a computer simulation of what we would have seen if we were close. So you can see the 2 black holes. I hope you see my cursor. You see the 2 black disks orbiting each other, and then you see the stars behind appear to move around in a crazy and rather complicated pattern. And as we watch, the motion of the two black holes is going to speed up. And then rather suddenly they merge, leaving only a single black hole. And some more details we might comment on in a little bit. So one thing you might notice is that the black holes do look like black holes in space. That's because they block light coming from behind. So in this picture, gosh, I myself can't see my cursor at the moment. On the right of the picture, I've drawn an eye. I can't really pinpoint it because for some reason the cursor isn't showing up. I'm not sure why. On the right of the picture is the eye. In the middle is the black hole, and behind it, schematically shown in red, is a star. So we're trying to look at the star, but light that would come directly to the eye from the black hole, from the star, actually disappears into the black hole and we don't see it. So we don't see the star directly behind the black hole. That doesn't mean we don't see the star, however. We see it because of the way light is bent by the gravitational field of the black hole. So in this picture, I've drawn a light ray that does reach the eye from the star. It's shown in red. The curved red line is the orbit of a light ray that goes from the star to the eye, and it's bent above the black hole. So we'd see that star, but we wouldn't see it where it really is, so to speak. I've put the words really in quotation marks because in relativity theory, it's a little bit subtle where something really is. But intuitively, when the light reaches us on the curved path shown in brown, we would extrapolate back, and thinking it came on a straight line, we would think its actual position was the one shown in pink, up above. So the apparent position of the star is way up above its actual position behind the black hole. I've explained this as if we just see one image of any star, but actually we will see multiple images of the same star. That's most obvious if the star is symmetrically placed behind the black hole. So here I've drawn two rays that reach the observer from the star. One shown in brown goes above the black hole, one shown in brown goes below the black hole. So we'd see two images. But with a little bit of imagination, you might be able to see that if the star is really symmetrically placed behind the black hole, we'll see a ring known as an Einstein ring. That will only work if the star is precisely behind the center of the black hole. If it's a little bit off center, we will just see two images, one above and one below. So I'll discuss later what we have in terms of pictures of black holes. But our best Einstein ring picture shows an Einstein ring caused by a galaxy, a galaxy bending the light rather than a black hole bending the light. So here I've shown a very unusual picture taken by the Hubble Space Telescope. So in whitish yellow at the center of the picture, you see a black hole which is you see a galaxy which is behaving as a gravitational lens bending distant light. Then around it, you see an almost perfect circle. Well, you don't see a complete circle. The part at the top is missing, and the part you can see isn't a perfect circle. It has more structure. But in blue, you can see most of a circle surrounding the yellow galaxy. That blue is an almost complete Einstein ring. It's an image of a blue galaxy that's made by the yellow galaxy in the foreground. The blue ring is actually an image of a blue galaxy that's behind the yellow galaxy. And because it is behind, the light from the blue galaxy has been deflected and bent into most of an Einstein ring. The blue galaxy is blue because of the temperature or color of the stars making it up. They're hot, so they look blue. Now, this picture with an almost complete Einstein ring is not a typical Hubble Space Telescope picture. It's a lucky one. In a moment, I'm going to show you a more typical picture. This is a more typical Hubble deep field photo. Deep field just means that they've zoomed in on a very small portion of the sky. They took a very long exposure, so very faint distant galaxies show up. And most of the galaxies have this yellowish gold color, but you can also see some partial Einstein rings that look like arcs. Again, I'm not sure why, but my cursor isn't showing up, so I can't pinpoint them. But if you look at this picture, I think near the center you'll see an orangish red arc, and at other places you see various bluish white arcs. They're partial arcs. They're pieces of Einstein rings that we're seeing because a foreground galaxy, one of these whitish gold galaxies, is lensing the light of a more distant galaxy, producing an arc which is part of what would be a perfect Einstein ring if the geometry were more perfect. So this is what it looks like when a object closer to us is bending and deflecting the light of a more distant object. Now, before we look at the movie one more time, we're going to discuss a few basic things. So first, the two black holes at the beginning are orbiting each other, a little like the Earth orbiting the Sun, except unlike the Earth, which is much lighter than the Sun, here the two black holes have almost the same masses. As they're orbiting each other, they're accelerating. And so in physics, we understand that to keep two bodies in orbit rather than flying apart, they have to keep accelerating toward each other. And that acceleration makes them emit gravitational radiation, which LIGO detected. That causes them to lose energy and fall in. Eventually, they merge into a single black hole. Finally, as the black holes move around, the stars behind them, the star field behind them is greatly distorted by the bending of light by the black holes. So with that understood, we'll watch the movie one more time. The black holes are orbiting around each other, greatly distorting the star field behind them in a way that's really quite complicated. But as the two, well, even before the two black holes merge, you can see that there's a sort of oval ring around them where the stars look like they're flying around in orbit. And it simplifies now. There's a circle of stars. Okay, it all dies down toward the end, but the circle of stars was actually what was left of an Einstein ring. The stars we were seeing were not exactly behind the black hole. So their images were not formed into rings. But what you see from stars that is almost exactly behind the black holes is very sensitive to exactly where it is. And that's why there was a ring toward the end of the movie where the image is very unstable. So I'm just showing this movie one more time. And at the end of the movie, you're going to see a ring on which the star positions keep oscillating. Anyway, this is what the LIGO event would have looked like if you were a few thousand kilometers away. Now, why is light deflected by gravity? Actually, Einstein guessed this before he had invented his theory. He knew that a comet or a planet is deflected by gravity, so he thought it would happen for light. Since Newton's day, scientists had known that the deflection of an ordinary body, for instance, a comet by the sun, depends only on its velocity and not on the mass of a comet. Here I've drawn schematically a fast object that's deflected a little bit by the sun and a slower object that's deflected by more. Well, in 1911, before developing his theory, Einstein guessed that the same effect would hold for light using the speed of light in Newton's formulas. The effect was so small it could only be observed during a total eclipse of the sun. So astronomers went off to try to test his prediction that the apparent position of a star would be different when it was very near a sun during a total eclipse. You need to see, the effect is so small that you can only see it for a star very close to the sun. But the sun is so bright that you can only see stars that are very close to the sun during a total eclipse. So people tried to test Einstein's prediction starting in 1912. Einstein was lucky, though at first it looked like bad luck. An attempt to test his idea in Brazil in 1912 was ruined by rain, and an attempt in 1914 in Russia was thwarted by the beginning of World War I. In fact, the astronomers came close to being arrested as spies because their telescopes looked like spy equipment to the Russian police. In 1915, Einstein finally developed his theory, and it became clear that the Newtonian formula that he had suggested before was 2 times too small. Luckily, his original prediction had not been tested. Finally, after the war, science resumed, and the eclipse expedition of 1919 confirmed Einstein's prediction. This was actually the event that made Einstein a household name. His name was well known among scientists before 1919, but not among the general public. For example, here's how the New York Times event reported the event on November the 10th, 1919. Lights all askew in the heavens. Man of science, man here, more or less agog over results of eclipse observations. Einstein's theory triumphs. Stars not where they seemed or were calculated to be, but nobody need worry. A book for 12 wise men. No more in all the world could comprehend it, said Einstein, uh, as his daring publishers accepted it. The statement that no more than 12 could comprehend it, was an exaggeration in 1919, and it's certainly a far exaggeration today. All of you on the call on this webinar who are physics students, if you go on a little bit, certainly can understand Einstein's theory. Einstein's theory was based on reinterpreting gravity in terms of curvature of space-time caused by mass. So it's hard to really draw a picture because it's very important that what's curved is space-time, not just space. And although we can draw the curvature of space, we can't really draw the curvature of space-time. So this is a picture where space was visualized as being two-dimensional, a trampoline, and the Earth is visualized as a ball that weighs down on the trampoline, causing it to be bent. That's about as well as you can do for drawing a simple intuitive picture of the curvature of space-time caused by mass. So when we think about a black hole, we should think of a highly curved region of space-time. I'm going to show next another movie of the LIGO event, which tries to help us visualize how space-time is curved, as opposed to showing what we would see if we were there, which is what the first movie showed. When you're watching this movie, note the time and the display. So in this movie, the black hole is just shown as a black ball, and that is only in there to show you where the black hole is. What you're really supposed to look at is the space-time around the black hole. Okay. This is the starting point. It's minus 0.76 seconds. My cursor is back. I don't know why. So minus 76 seconds before the start. And you can see a tiny black dot. Those are the black holes. And underneath them, what you're really supposed to look at, shown in blue, red, blue, yellow, and black, is meant to be the curved space caused by the black hole. We'll zoom in on it in a moment. In general relativity, the region of curved space is the black hole. There's nothing else. The black dots that are shown there are only put there in the movie to tell you where to look. And very faint out here are the gravitational waves that are already beginning to be created by this pair of black holes as they orbit each other. And below was sketched the gravitational waveform, which is slow in the beginning and then will speed up toward the end of the movie. Now we watch the movie, and you can see the regions of strong curvature are orbiting each other, and now we're starting to zoom in on it. Sorry. Okay, I accidentally stopped the movie. We're going to watch it again. The regions of strong curvature are orbiting each other, and we zoom in on them, so we're going to see closer. So now you see what look like pits, where space is very closed, very curved, underneath those orbiting black balls. Again, the black balls aren't really there. They're just a way to tell you that that's where the black hole is. What really is the black hole is just the region of strong curvature underneath those black bodies. We're now 0.23 seconds before the final collision, and the orbits are speeding up. They're going to speed up more, and the movie will be slowed down toward the very end. So now we're 0.015 seconds before the final collision. The two black holes are merging, and the movie's been slowed down very much. It's even frozen here. And then when it resumes, there's only a single black hole, and in pink and blue, you see the outgoing gravitational waves. And now we're 0.02 seconds after, 0.04 seconds after the event. Now we've zoomed out, and you see the gravitational waves going off to infinity, where they'll reach Earth a billion years later. We're going to watch the movie one more time. I won't explain it again. I'll just let you watch it this time. Okay, this is after the event, so we're just seeing at the end a single black hole with the ripples of gravitational waves going off to infinity. Now, at the end of the movie, hopefully you saw the outgoing ripples that represent gravitational waves. Well, why are there gravitational waves? If I move an ore in the water, I create water waves. If I take an electrically charged body and shake it, I create electromagnetic waves, which become radio waves or waves of visible light if the shaking is fast enough. According to Einstein, if I shake a mass, I create gravitational waves. But Einstein and his contemporaries thought that this fundamental prediction would never be tested because gravitational waves interact so weakly. Einstein and his contemporaries did not anticipate the technology that made LIGO possible, and they also did not anticipate such powerful sources of gravitational waves as the merger of two black holes. I'm going to show another movie that emphasizes the gravitational waves that come out of the event. So here are the two black holes orbiting each other. You see faintly in green going off the waves, and the wave signal is going to become stronger and faster as they orbit more rapidly. So now we're getting close to the end, and that's the signal that ultimately is detected on Earth. How strong was the gravitational wave created by this event? One way to measure that is to ask how much energy it carries. Astronomers depict the mass of the sun by what I've drawn here. This M with the astrological symbol. That black dot surrounded by a circle was originally a symbol used in astrology. It's still used in astronomy today to represent the sun. So M with that symbol is the mass of the sun. The black holes that merged in the LIGO event had estimated masses of 29 and 36 times the masses of the sun, but the final black hole had an estimated mass of 62 times the mass of the sun. As you can see, a mass of 3 times the mass of the sun disappeared. What this actually means is that 3 times the mass of the sun was converted into gravitational waves. The energy of the gravitational waves was 3 mc squared. About a billion years later, the gravitational wave arrived at Earth, and this is going to be a cartoon of what happened. And as they show at the bottom, the scale of the effect is vastly exaggerated. When I've shown this movie to live audiences, it sometimes produces laughter. A passing gravitational wave made the Earth vibrate, but by an amount that's imperceptible in ordinary terms. It's greatly exaggerated by a factor of more than a billion in this movie. So, okay, you can see in green a gravitational wave passing the Earth is starting to vibrate, vastly exaggerated. And as we get nearer the end, the Earth vibrates faster and faster and more widely, and then it stops when the wave passes. So how was this observed? Because this was a vastly exaggerated effect. Well, it was observed by the LIGO observatory, which really consists of 2 observatories. What's photographed here from the air is the one in Washington State, in the northwest of the United States. The other one is in Louisiana. What it consists of, there are 2 tunnels. I'm not sure why, but I get and lose my cursor. So again, it's not working. There are two tunnels, one on the right, one on the left. They each have a length of about 3 kilometers. I can't highlight them, but I hope you realize that the white lines you see in the picture are these tunnels. Each tunnel is about 4 kilometers long, and it has mirrors at each end. And bouncing back and forth between those two mirrors is a laser beam. Now, the length of the um, tunnels changes slightly because of the passing gravitational wave. It changes by about 1 part in 10 to the 20, which, given the length of the tunnels, means it's changing by something like 10 to the minus 15 centimeters. Now, that's a very small distance, but as the laser, okay, then there are laser waves bouncing back and forth in each tunnel, and at the near end, at this bottom end where you can see some buildings, there are half-silvered mirrors, and the laser beam has the chance of escaping from either the left tunnel or the right tunnel and being recombined. And in building this observatory, it's been arranged so that when the signals recombine, there's a negative interference and you see nothing, unless there's a passing gravitational wave, which slightly changes the length of one tunnel compared to the other and causes the two beams to be out of phase with each other. So there are very, very many laser photons bouncing up and down in the two tunnels, and with very small probability, a laser photon escapes and is observed, provided a gravitational wave has changed the length of one tunnel relative to the other. So then finally, in this picture, I've shown the raw data from the two observatories in Washington and in Louisiana. The reason the two observatories were built was because gravitational waves are a completely new phenomenon, to make sure what was being seen really comes from space rather than from a local disturbance like a passing truck causing one of the observatories to vibrate. So you can see, well, in red on the upper left is the raw signal from Hanford, Washington. On the upper right, in red on the upper right is the raw signal from Livingston, Louisiana. Now, near the beginning, we're mostly seeing noise. So you can see that the noise amplitude is roughly 0.5 in these units. And there isn't much correlation between the noise so on the right in blue is the signal from Hanford superposed on top of the red signal on the right. So you can see that at the beginning, the signals are not well correlated with each other. We're mostly seeing noise. You can also see that when the signal becomes larger, it's also highly correlated between the two observatories. And there's a period of about 0.07 seconds where we really are seeing gravitational waves and the signals from the two observatories are correlated. Then it ends and we go back to seeing noise. By 0.45 seconds, we're seeing noise. To make these two agree, the Hanford signal has been shifted relative to the Livingston signal by 0.07 seconds, which is the extra time it takes for a gravity wave traveling at the speed of light to get to Livingston versus Hanford. What's shown at the bottom is a fit based on general relativity to the actual gravitational wave signal that would be observed at the two observatories. It's slightly different at the two because they're oriented differently. And if you compare the theoretical signals to the observed signals, that'll also give you another reading of how big is the noise at the two observatories. So that's as much as I'll say about the signal that was observed. There's something else I want to say about how light interacts with the black hole. That's the one thing most people hear first, but that I haven't explained yet. So in explaining it, I'm going to take another look at a black hole. I'm going to emphasize a black hole as a static object that exists in space. So I've drawn space horizontally and time runs vertically. And I think of a black hole as an object that's sitting still in space at all times. So it sweeps out a tube in space-time that I've indicated in black. And now here's a different picture of a light ray. A light ray travels at the speed of light, but I've chosen units so that the speed of light corresponds to a 45-degree angle from the vertical. In other words, I've chosen units where the speed of light is 1 unit of space in 1 unit of time, and therefore a 45-degree angle from the vertical. So here's a light ray escaping from near a black hole. When it's close, it moves slower than the speed of light relative to the black hole. Einstein would say that in a local inertial frame, it moves at the speed of light. But in a frame where the black hole is at rest, it moves slowly at the beginning, which corresponds to moving almost vertically. But as it escapes, it starts moving at a 45-degree angle, because as it escapes, it ultimately is moving effectively at the speed of light in vacuum. Now here I've shown light rays that are closer and closer to the black hole. The ones that are closer to the black hole are slower to escape. So they move almost vertically for longer, and it takes longer before they start moving at almost a 45-degree angle from the vertical. And a light ray that's very close to the black hole is very nearly vertical. And finally, a light ray at the surface of the black hole, what's called its horizon, never escapes. It just moves vertically, which I've tried to indicate by drawing in reddish brown a light ray that just goes in the time direction with no motion in space, just parallel to the black hole surface. And finally, although I didn't draw them, light rays in the interior of the black hole just collapse inward toward the origin. So all the pictures I've shown you, both crude drawings like this one and the movies we had earlier, of what's happening near a black hole, were simulations of some kind. Could we take a real picture of a black hole? Well, what determines how big something has to be at a given distance so we can see it? And when I say seeing an object, I mean not just seeing that it's emitting some light, but seeing something about its structure so that it looks like more than just a point. The fundamental limit comes from the wavelength of light divided by the size of the lens. For example, visible light has a wavelength of about 1/20,000 centimeters. Your eye has an aperture of about 1/3 of a centimeter. So if you take the ratio, we learned that your eye has an angular resolution of about 1/80th of a degree. Anything with an angular size smaller than 1/80th of a degree will just look like a point, even under ideal conditions. When I say it just looks like a point, it'll look the same a point would have looked. It'll have an apparent size of 1/80th of a degree, because even a point would have an apparent size to your eye of 1/80th of a degree. So something has to be bigger in angular size than 1/80th of a degree for your eye to see it as anything different from what a point would look like. For example, the planet Jupiter at its closest has an angular size of about 1/80th of a degree. If it were just a little bit bigger or closer, you could begin to resolve it with the naked eye. That's why the planets can be resolved by even very simple telescopes, such as the one available to Galileo. The eye can almost resolve the planet Jupiter, and Mars and Venus are not too much worse. So even a very simple telescope will enable you to see that Jupiter, Saturn, Mars, and Venus are not just points, but little disks. A simple amateur telescope has a resolving power roughly 25 times better than the naked eye. So that means that instead of 1/80th of a degree, the simple amateur telescope will let you resolve something whose angular size is roughly 25 times less than 1/80th of a degree. How much better are the telescopes used by professionals? Much better for seeing faint objects, but except for some modern tricks, not much better for resolving objects with a small angular size. That's because of the turbulence of the Earth's atmosphere, and it's the reason for launching the Hubble Space Telescope, whose resolving power is roughly, 10 times better than a simple amateur telescope, and therefore, I think 250 times that of the naked eye. And nowadays, apart from the Hubble Space Telescope, for many purposes, we can also get a similar resolution with what's called adaptive optics, where special tricks are used to fight the turbulence of the Earth's atmosphere. So what if we want to take a picture of a star and directly measure its size? Well, the star with the largest apparent size as seen from Earth is Betelgeuse, with an angular size of 1 over 50 million degrees. Way too small even for the Hubble. Betelgeuse is not particularly close, but it's a red supergiant near the end of its life, and red supergiants are very big as stars go. So Betelgeuse is an enormous star. I think its size is comparable to the distance from the Earth to the Sun, but I'm forgetting. I hope I'm not exaggerating. It's not particularly close. It's very bright, but if you want to see it, it's one of the shoulders of the constellation Orion. Orion, I'm not certain if Orion goes by the same name in Bangladesh, but Orion is one of the easiest to see constellations in the northern hemisphere, actually even in the southern hemisphere. And Betelgeuse is one of its shoulders. I think it's the upper right shoulder as seen in the northern hemisphere. So Betelgeuse is way too small, even for the Hubble. But there is a way. Well, there are a few ways. There are some tricks to fight even with conventional telescopes. But because of its application to black holes, the trick I'll tell you about is interferometry. Using the wave nature of light, you can combine the signals collected by different telescopes and get a huge resolving power. So here's a picture of Betelgeuse. This is an actual picture. It was taken by the Alma Array in Chile, in the southern hemisphere, which I'll describe in a moment. I don't think it's very well understood what this picture is showing, but the structure it's showing is real. So that bump on the left is real. And the whitish spot is also real. So the structure that you see in the picture is believed to be part of a real picture of Betelgeuse. And since this is the best picture we don't have that much detail. But here's a picture of the Alma Array. It's an array of radio telescopes, and since they use radio waves, that by itself, since the wavelength is longer, would give worse resolving power than we get in visible light, as with the Hubble or with a simple amateur telescope. But the trick is that they use interferometry. So here I've shown, this picture shows two telescopes in the Alma Array that are roughly 80 to 100 meters apart. But the array stretches over a number of kilometers. And the radio signals received by these different telescopes are combined coherently, and they're made to interfere. That means you see the wave patterns produced by combining the waves from different telescopes. And with such an interferometry, you can get a resolving power much better than you could get from a single telescope in the array. So ALMA is the equivalent for its resolving power of a radio telescope whose size would be the size of the whole array, about 5 kilometers. So with a 5-kilometer radio telescope, you can produce this picture of Betelgeuse. Betelgeuse has had a weird behavior in the last year. I wrote the last few months, but by now it's the last year. And there was a lot of speculation. I'm not sure how well it's understood even now. Its brightness fluctuated by a lot. It dimmed a lot, and then it's recovered in brightness more recently. I think it's believed that it emitted a cloud of gas which condensed into dust that blocked some of the light from the star in our direction. Anyway, it's had a very weird behavior in the last year or two. Now, before I get back to black holes, I'm going to ask a question. Given that stars have an angular size way below the resolving power of the human eye, why do bright stars look bigger than faint stars? First, I'm going to assume that you all know this. If it's not clear to anyone, then the next time you're in a good place for observing the stars, just look at the stars, and you will see that the bright stars look bigger than the faint stars. But the answer, I'm sorry to tell you, has nothing to do with the actual sizes or distances of the stars. It's purely a question of the limitations of the human eye. So if you look at a point source of light, imagine a star so distant that we can think of it as a point source of light. Because of the limited resolving power of your eye, the light you see, roughly speaking, will be spread over an 80th of a degree. But that's an approximation. There'll be more light toward the center and less farther away. And how far out into that distribution you can see depends on how bright the star is. So for a faint star, you actually only see the very brightest part of the distribution. But for a brighter star, you'll see out into the tail of the distribution. You'll see more, so you'll see more than an 80th of a degree for the brightest stars. Now, anyway, let's go back to black holes, and suppose we want to take a picture, not of a star, but of a black hole. The largest black holes as seen from Earth are two, actually. One is at the center of the Milky Way, and the other is at the center of a distant galaxy known as M87. The name M87 is probably not familiar unless you're an amateur astronomer or maybe a professional astronomer, but it's actually one of the easiest galaxies to observe from Earth. You can see it with difficulty in a relatively simple amateur telescope. This is a picture of M87 of sorts. I think this is a combination of different kinds of pictures from different telescopes. So it was observed roughly a century ago, originally in optical light. A century ago, radio telescopes didn't exist. So astronomy meant optical astronomy. And a century ago, an optical observer saw that M87 looked like a fuzzy ball, but it wasn't completely symmetrical. There was something odd on one side. Here's a better modern picture. Yes, it's a fuzzy ball, a so-called elliptical galaxy, brighter in the center, but surrounded by a fuzzy ball of stars. But there's something coming out of it on one side, which in this picture is depicted in blue with some knots of greater density. And in the modern understanding, that's a jet of matter that's been emitted from the black hole. It's actually not very well understood what's happening in detail. It's believed that there's a massive black hole at the center of the galaxy, a mass of a few billion solar masses. Surrounding it is a disk of matter, a disk of hot matter, which generally is spiraling in, but some of it escapes along the poles. And it's believed we're seeing a jet of matter escaping along the pole of the rotating black hole. It's believed there's a second jet in the opposite direction away from us. We're not seeing it in this picture. The jet, because of the Doppler effect and also because the galaxy itself blocks a lot of the image, the jet that's going toward us is much more visible than the jet going away from us. But it's believed that depicted in blue here, with a little bit of white, is a jet that's going almost in our direction from the black hole, and that there's an equivalent jet in the opposite direction. Now, the black hole in M87, and likewise the one at the center of the Milky Way, has an angular size about 1,000 times less than that of Beetlejuice. So it takes an array of telescopes with about 1,000 times the size of Alma to take a picture of the black hole in M87. Now, the array of telescopes in Alma has a size of roughly 5 to 10 kilometers. So now we want, multiply that by 1,000, we need an array of telescopes working together whose size is roughly the size of the whole Earth. Such an array has actually been constructed, the Event Horizon Telescope, it's called. Their first picture of the black hole in M87 was published I wrote just this last year, but I think by now it's closer to 2 years ago. It's still the only real picture we have of a black hole, or more precisely, its environment. This is the picture. It was widely covered in the news when the picture was taken, so you might have seen it in the news in Bangladesh or elsewhere. And this is our only picture of a black hole, and the fact is we don't understand very well what it's showing. We understand roughly what it's showing. In the center, we see the black hole, and around it, we see a ring of matter. And as I explained at the beginning of the talk, matter behind the black hole is bent into a ring that we see. Okay. Well, it's believed that there really is a ring of matter around the black hole, rotating around the black hole. But in addition, the bending of light by the black hole has a big effect on what we see. So the ring we see is partly there because there really is a ring, and partly because of the gravitational field of the black hole. The fact is we don't have enough information yet to disentangle what's going on in that picture. It's just a first picture of a black hole, and we need more to understand exactly what's happening. There's a lot going on in that picture. The black hole is rotating, there's matter around it. The details of the matter aren't known. We don't know how strong is the magnetic field. We don't know how the matter is distributed. So we've got a long way to go to understand in detail what's happening. But roughly, we're seeing an Einstein ring created by the black hole in M87. One obvious question, why is the bottom part of the ring brighter? It's probably because of a mixture of the rotation of the black hole and the matter around it. And hopefully we'll come to understand that better due to more data. To get this picture, they used telescopes in Chile, Arizona, Hawaii, Europe, and the South Pole. There's a planned upgrade with the new telescope in Greenland. In fact, by now I think the telescope in Greenland may be working. It's also possible to do a little better by using radio waves of a somewhat shorter wavelength. For a big improvement, go to space. For example, if you put a radio telescope on the moon and you're able to do interferometry, combining the signal of radio telescope on the moon to a radio telescope on Earth, you could do a lot better in principle. These radio telescopes collect so much data, but they're not able to communicate in real time. There's too much data. They collect the data on hard drives, and they need to have very precise timing information. So they use atomic clocks to tell the time very precisely. Then, after the fact, they fly these hard drives to a combined location and combine the signals with supercomputers and eventually produce this picture. If you have a radio telescope on the far side of the moon, you're going to need to fly the data back to space. You're not going to be able to send all that data from the moon back to space by radio. It's just too much. So that isn't for tomorrow. You don't have to go to the far side of the moon. The far side of the moon is a good place because you avoid radio interference from Earth. You could simply have a telescope maybe 1,000,000 kilometers from the Earth. You still would have to send the hard disks back to Earth, I think. I don't think you could send them all that data back by radio. I'm going to end with one more movie. This is a simulation of what we would see when a black hole passes through a galaxy. Well, in the movie, the black hole is moving at a mildly relativistic velocity, something like 0.1 the speed of light, but not 0.99 the speed of light. So the event takes hundreds of thousands of years. So the movie shows what we'd see when a black hole passes through a galaxy if we could live for hundreds of thousands of years to watch it. And we're watching it from a distance of roughly 100,000 light years. In the beginning, the way you'll see the black hole is that there's a ring of light around the black hole. That's because light from the galaxy that passes close enough to the black hole can be bent in our direction, producing a ring, a sort of lopsided version of an Einstein ring. As the black hole passes through the galaxy, the image of the galaxy will be massively distorted by the black hole. Then it will pass through, and again, as the black hole departs on the other side, we'll see a ring of light surrounding the black hole. Anyway, okay, here we are before we start. In the upper, okay, my cursor's working again. In the upper right is the galaxy. This is the central part. And you see in reddish brown the gas and dust and stars of the black hole. Of the galaxy. Down here is the galaxy, and around it you see a ring of light. The ring is mostly on the far side because light is more likely to be bent around the black hole in our direction than to be bent in front of the black hole in our direction. Now, as we watch the movie, the black hole is passing through the galaxy, and now as it passes through the other side, again, we only see a ring that's visible mostly on the far side from the galaxy. This movie actually repeats again, so I'll let it play a second time. I wish my cursor had worked during some of the other movies. So I guess that's what I have to offer for you today. I've tried to show you something about some of the exciting observations of black holes in recent years. We've talked about the observations of gravitational waves by the LIGO Observatory, and I've also explained a little bit about the first picture the first picture of the environment of a black hole that was taken by the Event Horizon Telescope just in the last couple of years. Thank you very much for your attention.
Thank you, sir, for your wonderful and exciting lecture, sir. So we have got few questions. So if you allow, we can start our discussion session.
That would be great. Yes, thank you.
Yeah, and I can add question in the screen. If you stop share, then you can also see this question.
Okay.
Okay, the first question. So, do fuzzy ball theory in string theory replaces the singularity of the black hole by a ball of strings? And can it solve the mystery about how particles behave outside a black hole, photon sphere?
Well, first of all, I want to say that the fuzzball theory is very speculative, but what it would, well, it would replace the black hole interior by a ball of strings, roughly. So the replace the change. What I want to slightly correct your statement. The fuzzball theory replaces not just the singularity, but even the horizon of a black hole by a ball of strings. So today we've been looking at a black hole from the outside, and we can't see beyond the horizon. So I've only really today talked about the horizon and what's outside of it. But the fuzzball theory would replace the interior of a black hole with a ball of strings of some kind. It's unknown whether it has observational consequences. Some, I think it's highly optimistic, and personally I think it's unlikely, but some people working on fuzzballs are optimistic that changing the nature of the black hole horizon will actually have observational consequences as seen from the outside.
Sir, thank you. We have another question. So, sir, which one is more compatible, string theory or quantum loop gravity?
Well, personally, I think that string theory is a much more serious and interesting theory. String theory has gotten interesting results in all kinds of different areas. It's shed a lot of light on existing theories of physics. It's done a lot that's highly non-trivial in quantum gravity, and it's shed a lot of light on other areas of mathematics. So, in my personal opinion, the answer is clear. However, if you want to work in one of those areas, then as you learn more, you have to form your own opinion and decide for yourself as you get deeper into it.
Sir, thank you. We have another question, sir. When we talk about the quantum vacuum, does it mean there is nothing, or rather it means there is energy and fields? Because there is a book named Universe from Nothing.
Energy and fields are a better description. The quantum vacuum is really very subtle, and this is shown most clearly in the theory of strong interactions. Because in the strong interactions, according to the strong interaction theory, quantum chromodynamics, ordinary particles like protons and neutrons are really made out of quarks and gluons. But what we see are not individual quarks and gluons. We see them combined into particles like protons and neutrons that don't carry the color charge. They are phenomena called confinement and chiral symmetry breaking. And those phenomena reflect the nature of the quantum vacuum. So as this example shows, the quantum vacuum can be highly non-trivial and contain a lot of information. So it contains energy and fields, but it contains a very, very subtle and in general difficult to understand configuration of energy and fields. One of the main problems of physics really is to understand the quantum vacuum. So you're quite right with this question. Vacuum definitely does not mean nothing.
Thank you, sir. Now we have another question. So, what role cosmic neutrinos could play in identifying black holes?
Well, we've seen, let's see, I think the best answer is that we've observed a burst of neutrinos from a supernova. And that supernova event was not collapsing to a black hole, it was collapsing to a neutron star. But some supernovas do collapse to black holes. So we could see a burst of neutrinos, if we're lucky, from an event where a black hole is forming, and it would certainly give us information about that event. And LIGO, the original LIGO event was that collision of two black holes, but LIGO has also observed a collision of two neutron stars. And theoretically, a collision of two neutron stars would create a neutrino burst. Unfortunately, that event was much too far for us to observe it with our neutrino detectors. But in principle, we could observe the neutrino burst from that event that LIGO has actually seen if it were closer. And that would certainly be an interesting way to observe that event. I think that's the best I can do to answer that question.
Thank you, sir. Now we have another question, sir. What is your comment on information paradox in black hole?
So,
Very
it's a very
interesting.
exciting question. So, before, so it's been extremely difficult to really understand what black holes mean in the context of quantum mechanics. The modern version of that question is called the information paradox. So, Stephen Hawking showed that at the quantum level, black holes evaporate. And it's been difficult to understand how that's consistent with this conventional laws of quantum mechanics, according to which the evolution should be unitary. The evidence is that it is unitary, but we don't understand it very well. And this is really a question at the research frontier. Uh, if you, if at your university you want a question that's a lecture, I should say, that's a little bit more specialized and research oriented, then someday I could give a lecture on quantum, on uh, black hole evaporation, and a modern point of view about it.
Okay, sir, thank you. There is another question. So, do Planck length size black holes exist where its Compton wavelength and Schwarzschild radius are approximately the same?
Well, presumably something like that is true, but we don't know if you can literally get down to the Planck length. For example, in weakly coupled string theory, once you get down to the string scale, which is a little bit bigger than the Planck scale, you wouldn't have a black hole anymore. It would turn into a gas of strings. So that's one possibility of a slight correction to what you've said. Something roughly like what you've said is going to be true, though. Black holes can certainly be much smaller than the ones we observe in nature.
Yes, sir, thank you. There is another question from Abdullah. Sir, can we make artificial black hole in the lab?
That's a great question, but unfortunately, with any foreseeable technology, the answer is no. It would take, I don't think 22nd century technology would be enough. It would be incredible to be able to make artificial black holes. And if you could, you certainly would be able to learn a lot about physics that we can't learn with the experiments we're actually able to do.
So thank you, sir. Actually, Abdullah is a school student, and he's very fond of in high energy physics and in astrophysics, and so he wants to know more about this field. So thanks, Abdullah, for asking questions. So there is another question, sir. What is the uses of tetrad formalism and Newman-Penrose formalism in black hole mechanics?
That question's a little hard to answer because there are various applications. The one I care about most is that the tetrad formalism was needed to describe spinors or spin half particles in gravity. But that's by no means the only application. Some people would have given different answers.
Okay, sir. Thank you. And again from Abdullah. So, sir, I am a student of class 10, and can you please explain to me about quantum fields?
I don't know what class n means, but it's also hard. Quantum fields are too big a subject to explain just while standing here. It's a subject for a course. But the basic idea, first people discovered quantum mechanics. They had point particles like the electron. Why doesn't the electron spiral into the atomic nucleus? Well, it doesn't because it obeys quantum mechanical laws. But after the Schrodinger equation was invented, people realized that there also are electromagnetic waves. And if quantum mechanics is applied to point particles, we should also apply it to waves. And quantum field theory is the theory where you treat waves or fields quantum mechanically. But I think for more information, you really need to take a course. Well, gravitational waves can reach Earth, and we observe them. That's what the LIGO detector observed.
Yes, sir. There is another question. Can these gravitational waves reach Earth? Yeah, you have already explained.
Yes.
And there is another question. So, if there are supermassive black holes, what is the smallest black hole? And also, how small can black hole get?
Well, that's a great question. And It's somewhat related to one of the previous questions. As one of the other questioners suggested, it might be that black holes can get all the way down to the Planck mass, which would mean a mass of about 10 to the minus 5 grams and a size of about 10 to the minus 33 centimeters. But that's beyond our knowledge of physics. It might be that the lightest a black hole can be is somewhat heavier than 10 to the minus 5 grams.
Thank you, sir. There is another question. So, uh, how would you differentiate the gravitational wave signal coming from a stellar mass black hole and IM black hole and supermassive black hole neutron star mergers? And is there any specific category for each of them?
Well, this is a great question, but actually a very big question. I'm only going to answer the simple part. Well, I'll say a couple of things. First of all, LIGO has observed signals from black holes of different masses. They've seen signals from black holes of 5 solar masses, and the answer I showed you was from black holes of about 30 solar masses. As the mass of the black hole increases, a few things change. The orbits become slower, and the signal becomes bigger. So, um, bigger, so slower means lower frequency. So for a stellar mass black hole, the frequency is much higher, so the wave oscillates much faster, but its amplitude is much less. So when LIGO sees a collision of two 30 solar mass black holes, the signal was so big that when I showed you the raw data, you could see it by the eye. You only saw 6 oscillations, but there were about roughly 6, but you could see 6 very easily by the naked eye. Now, for a black hole with 5 solar masses, LIGO detects 1,000 oscillations, but the amplitude is less and is comparable to the noise level. So if I did not show you the raw data from a 5 solar mass black hole colliding with a 5 solar mass black hole, but the raw data wouldn't look like anything. It takes computer analysis to dig a signal out of noise. That's because the lighter black hole produces a weaker signal that's too weak for LIGO to see it above noise. But because the frequency is higher, LIGO can actually see it. Can't see it very well, but can see it at a level comparable to noise for 1,000 oscillations, not just 6. So a 5 solar mass black hole produces a completely different signal from a 30 solar mass black hole. Now, a supermassive black hole, LIGO can't see at all because the frequency is too low. So if you want to see a supermassive black hole, you have to go to space. And the Europeans have a project called LISA, which is supposed to be launched in 2032 and could see gravitational waves from supermassive black holes. I think I'll stick with that.
Yeah, thank you, sir. We have another question from Shujan sir. Sir, do you think a black hole or wormhole is physical or realistic? Does the warm travel is consistent with physics?
Well, I'm pretty sure warp travel isn't consistent with physics. Um, well, so precisely what to say about wormholes is actually a modern research topic. So in classical general relativity, you can have a wormhole, but you can't travel through it. The situation quantum mechanically is more subtle, and people are still studying it in the last few years. It might be possible for an elementary particle to get through a wormhole, but not a human. I think I'm going to stick with that answer under realistic assumptions.
Okay, thank you, sir. So we have few more questions. So if you have time, we can take those questions.
That's okay.
Okay. So there is another question. So do black hole form instantly? How long does it take for black holes to form?
Well, we saw a movie where two black holes combined into one, and the time it took for that is similar if you've been forming one black hole from a cloud of the same size, roughly. I think that's the best simple answer I can give. So
Okay, sir.
it's longer than just the time for the matter to fall in, because usually the matter, okay, under ideal conditions, if the matter was falling in a spherically symmetric fashion, the time for a black hole to form would just be the time for the matter to fall in. Realistically, there usually is some angular momentum will spin, and then the event will be more like that LIGO event. The objects orbit each other, and it takes a while for them to fall in.
Yeah, thank you, sir. There is a one question in chat box, private chat. I think you can also see in the chat box. So, what's your opinion on black hole magnetic field of new black hole pictures recently published? Is there another convincing way to detect gravitational waves more better? Thank you for your great lecture.
Well, thanks for the nice remark. Uh, Apart from the picture I showed, the Event Horizon Telescope published a second picture of the same black hole based on the same data, where they showed the polarization of the light. I'm not certain if that's what the question is asking about. If that's what the question is about, I'm not sure I can give a very good answer. Um, it shows information about the magnetic field, but also about the plasma outside the black hole that's producing that polarization. And I'm not certain how well understood it is or how much information it's given us about the black hole. If the question is about that picture, that's the best answer I can give.
Thank you, sir. We have another question. So, how long does it take for black holes to collide?
It depends on the mass of the black holes. But for black holes of 30 solar masses, I showed you a picture, which uh, I think it was annotated with the times. But uh, it's, well, it depends exactly what you mean by the question anyway. If if two black holes are heading head on for a collision, the time is just the time for them to fall in. I hope that the lecture has convinced you black holes are real. We showed a movie of black holes. We showed gravitational waves for black holes. The time to collide, if they're heading head on for a collision, it's just the time to fall. But if they're going to miss, then they'll orbit each other and spiral in. And then it depends on exactly what you want, because there's a final collision, which is fast, but the whole process is much slower. But I showed you some movies about it. For 30 solar mass black holes uh, colliding with a reasonable offset, there was 0.07 seconds of the final collision that LIGO observed. That's one answer.
Thank you, sir. I think you have answered this question already, so we can go to the next question. Sir, do black holes stay present infinitely? What is the final condition of a black hole?
Well, Stephen Hawking, that's a great question. In classical general relativity, black holes stay there forever. They can only grow. But Stephen Hawking taught us that actually, quantum mechanically, a black hole in empty space radiates and shrinks and would eventually disappear. We don't understand the details of how it would disappear, so I can't answer about the final condition. But one thing I do want to say is that black holes in the real world, in today's universe, are not in vacuum. Those LIGO black holes are in galaxies. There's matter. They're actually growing more from the matter they're absorbing than they're shrinking uh, from the Hawking radiation they emit. Thanks to Clyde Nathaniel for the kind remarks.
Thank you, sir. And there is another question. So it is said the first image
Yep.
of a black hole, very big question, of a black hole is formed a supermassive black hole at center of galaxy M87, which is 55 million light years from Earth. It is said there is another black hole that is nearest to Earth, about 1,000 light years away, called Acer 6819. And if it is said the naked eye can see it, won't the image be easier to create than the previous one, since it is closer? So why don't they took a picture of that?
Well, first of all, the image you mentioned is the one I showed in the talk. So we discussed and showed and talked about the image of M87, which, as you say, is 55 million light years away. It weighs about 5 billion solar masses. The black hole you talk about weighs about 5 solar masses. So it's a billion times lighter, which means a billion times smaller. But as you can see from your numbers, it's only 55,000 times closer. So if it's 55,000 times closer, but a billion times smaller, then its apparent size is much, much less, something like 20,000 times less. So they can't take a picture of that black hole because it's much too small, even though it's closer. As I remarked in my lecture, there is a black hole at the center of the Milky Way, which is better. It's tens of thousands of light years away. I don't remember the exact number, but it weighs a few million solar masses, and its angular size is about the same as the one in M87. And they're trying to take a picture of it. Um, the problem is that because it's smaller, the matter moves around it quicker, and the picture changes. Uh, so the picture of that object would be like a movie. It would be constantly changing. So even though the one in the Milky Way has the same apparent size as the one in M87, uh, the fact that it's changing makes it harder to take a picture. It's like trying to take a picture of children who are moving around. It's usually easier to take a picture of adults than children because the adults, when you're taking a picture, don't move so much. It's hard to get children to stand still, and that makes it hard to take a picture.
Okay, sir, thank you. We have another question. So, what is string theory?
Well, it's a kind of too big a question for right now. Great question, but too big for right now. But string theory is a theory. It's the framework where physicists have had some success in going beyond quantum field theory as a framework of physics. It replaces elementary particles by loops of vibrating string, and it unifies quantum mechanics with gravity. I think that's all I'll say for now. One day I could give another lecture uh, at this university and answer that question a little bit better.
Okay, sir. Thank you, sir. That will be very helpful. So, we have few questions. So, can we take this question? Maybe about
Well,
five.
I'd rather we can, but let's hear mostly questions from people who haven't asked questions yet.
Okay, so
So I'll answer quickly this one. We hope to, but we hope to find observational tests of string theory. But I would say it depends both on how lucky we are with the experiment and what the nature of the answer is, as well as how lucky and clever we are as theorists.
okay, thank you, sir. So, why there seems to be the supermassive black hole at a galactic nucleus? Since we can consider that the work of that black hole is to bind the glasses together, does this involve in the formation of a galaxy? In glasses with black holes in the center, what does its formation begins with, and what is the process?
Well, there seems to be a black hole at the center of the Milky Way because stars near the center of the Milky Way are moving so fast that we can't explain that except by the existence of a black hole with a mass of about 2 million times the mass of the sun. As for how it formed, we don't understand that. So your questions are great questions that astronomers mostly don't understand. We don't know how the black hole at the center of the Milky Way formed, and we don't know what role that played in the formation of the Milky Way.
Okay, sir. I have a few questions. What do you think about the each form qubit approach, and what does it mean for the universe to be made up of information?
Well,
Is that approach compatible with the string framework?
I actually think the it from qubit stuff is very exciting, the most exciting development currently in fundamental physics, in my opinion. I'm trying to get involved, although I haven't been too successful as of yet. I can't answer the second part, what it really means. And I expect it's compatible with string theory. Let me request that more questions should come from people who have not asked questions yet. If you've already asked questions, please don't ask more.
Okay, okay,
Uh,
sir.
okay, that last question I think was from Sarkar, I think has not asked questions yet. Maybe I'm wrong. So the G minus 2 experiment is a very important observation of the magnetic moment of the muon. Although I'm not an expert on the experiment, I tend to believe it because they're repeating a previous experiment and got the same answer after what appears basically, okay, they check the previous result. I tend to assume it's correct. However, I think it's not clear whether there really is a discrepancy from the standard model. The most recent computations in lattice gauge theory suggest that the standard model might be actually consistent with this observation. My guess is that that's how it will turn out, that the experiment is correct, but it might ultimately be consistent with the standard model. Because
Okay,
of
sir.
that, I won't answer the last part.
Yeah, thank you, sir. And there is another question. So, is it possible for a black hole to eat the entire galaxy?
It's possible for a black hole to eat an entire star, and the European LISA Observatory in space is expected to observe that process. Actually, I think we even have observations already, but not as direct as seeing the gravitational waves from that process. For a black hole to eat an entire galaxy, the black hole would have to be much bigger than the galaxy. And we don't know any black holes as big as that. So the question here is, suggest some books on general relativity. A classic textbook is the one by Robert Ward, and another one is the one by Steve Weinberg. So personally, I think most people starting to study general relativity would do well with one of those two books. Actually, there's some slightly more elementary books that I don't know, that I haven't used myself, so I can't say much about them. I think one is by Sean Carroll. You can look at them, but I can't tell you about them. Among books I myself have used, the two most useful are by Weinberg and Ward. And I also use the book by Misner, Thorne, and Wheeler, but I only use it for special purposes. It's hard to use systematically.
So, thank you. This may be the last question. So, how different are black holes at the galactic nuclei to those which exist independently?
Well, if I'm going to assume that by those exist independently, you mean things like stellar mass black holes that are formed in a supernova collapse of a star. So stellar mass black holes have masses of few solar masses, and masses in the centers of black holes at the center of galaxies have masses from a few million solar masses, like the one in the Milky Way, to a few billion, like the one in M87, or even tens of billions in some cases. So the difference is that they're much more massive. And another difference is we understand less about why they're there. We could say that the solar mass black holes we understand to some extent because we observe supernovas, and we're pretty sure that some supernovas collapse to black holes, but we haven't directly observed that yet. We expect to observe it yet directly, maybe probably through LIGO eventually. But we think we understand solar mass black holes, how they form. Maybe not all of them. There might be some that form in ways we don't understand. But black holes and galactic centers are more of a mystery why they're there.
So, thank you, sir, for your wonderful and exciting discussion session. So, I think it was a great webinar for our students and viewers. And they have learned a lot of things. And thanks again for giving us this opportunity to arrange such an important webinar. And thanks that you have told that you will talk about the string theory later. So that will be very great for our student. Thanks again, sir. It's my honor and privilege, sir, to host you in our international physics
Well,
webinar.
thank you, Pretam. I greatly appreciate this invitation, and I want to wish all success and good fortune to you and to everybody who's been attending this meeting. And thanks
Thanks.
to everyone for their patience, especially with the late start and
No,
the
no,
book.
it's okay, sir. It's our pleasure, sir. Sir, the main aim of our program actually is to motivate our student in this corona pandemic situation. And as you know that all the institutes have been shut down due to corona pandemic since last year, March 2020. So we are trying to do something to motivate and to encourage our students so that they can be well, feel well, and they can be fall in love in physics research and studies. So thanks, sir, for giving us this opportunity to attend such an important webinar with you.
Thank you again.
Yeah, bye,
So
sir.
long, well, everybody. So.
Okay, sir.